And Will, it has really kind of a stellar resume. He told me that I couldn't embarrass him by going through the whole thing. So I'm just going to tell you a little bit about him. He was a principal at Thornton Tomasetti Engineering in New York, one of the big kind of high-powered engineering firms in New York City. He was also a principal at Burrow Happold, also one of the big kind of design-oriented, R&D oriented engineering firms in New York City, and then went out a few years ago now, I guess 2 or 3 years ago now, and started his 3 years ago now, and started his own firm, which has particular emphasis on facade design, structural facade design, and what I would say, and Will might correct me, complex structural engineering, which is integrated with complex architectural and spatial ideas. That's my own words. Is that a kind of
Sounds
way
good.
of putting it? Also dealing a lot with technology. I think he's going to talk a little bit about some of his R&D work. But the thing that I love, and Will doesn't know what I'm going to say now, the thing that I found to be the best piece on the whole CV, you know, after the PhD research in London and Aachen and Barcelona, et cetera, is that he is a, I guess, licensed international welding engineer.
Yes, I did
which
that.
I find to be kind of fascinating, because I didn't even know it existed, and I
It does exist,
weld.
yes.
So, without further ado, I guess I would just say that both of these lectures are part of our unconventional practice series here at Georgia Tech, where we're trying to expand the field of what practice means post-architectural education, or maybe even during architectural education, and how you can start to sculpt and direct your education into something which might not look like the kind of archetype of what an architect or an engineer does in an office. Okay, so that's really the intent of this series, and we couldn't have better speakers today. So with that, I'm going to turn it over to Will, talk for maybe 45, 50 minutes, and then we'll have some time for conversation. Thanks.
Thank you, Tristan. Welcome, everybody. It's actually my first time at Georgia Tech, can you believe? After all those years I've been in the United States. So I'm honored to show up. My background is structural engineering, but I teach architects at Columbia University and at RPI. They gave me that Bedford professorship. So I'm a little bit in between those worlds where they overlap, engineering and architecture. And so despite my background, as Tristan said, I was handling quite some very large projects. Like I lived in Thailand, Bangkok, and I helped on the Bangkok International Airport with fabric structures and large steel arches. I'm more bringing projects that I feel are a bit more within reach, medium, small scale, and are in the overlap where engineering can support architectural design. So again, I did work for the King of Bahrain in the Middle East, and we built him a nice floating bank building together with SOM at the time. And that is my structural background. But I want to talk about something maybe a little bit more visionary, a little bit more provocative today. And there's a very nice saying, I put that right on the front page of our website, from George Bernard Shaw, and he says, "The reasonable man adapts himself to the world. The unreasonable one persists in trying to adapt the world to himself." And then you start giggling, but there comes another sentence, "Therefore all progress depends on the unreasonable man." Okay. So I brought biomimicry skins. A very close friend of mine, Marc Fornes, is now a celebrity artist all over the world. We are building metal skins that are free form and that follow the natural, non-geometrical shape. I want to show how these crazy little university things can become mainstream. We did pavilions in the LAX airport for Pinkberry, for Starbucks. I brought a new material, Ductal, which is a fiber concrete, where I'm actually working with Dex Industries right here in Atlanta. My friend Craig and I do a lot of projects which are very beautiful, using new concrete that no longer has rebar. And finally, I brought some cool stuff. We're working on the Culture Shed in New York and a few other things at the end. So the pitch on this first thing, we're not the only ones talking about biomimicry, is that biology inspires technology towards intelligent adaptive system design. And if we think about the time scale of millions of years nature's been around, only at some little pink deep the Homo sapiens us show up. And if you look at nature, you don't really find any 90-degree angles at all. So all we build right now seems to be man-made, seems to be geometrically driven. And what we're trying to say is with the modern software that Tristan also is an expert in, we're now no longer have to be hesitant about crazy shapes because we can handle digital fabrication, we can handle irregular forms. And if that is so, and we also have modern technology like 3D printing, and I get to that in a second, maybe we can shift away from geometrical 90-degree angle architecture and can learn from nature. This is how ants make a bridge, for example, or this is the elegant wing of an insect. And so actually when you look at our company logo, it is really based on the sunflower, and I chose it purposely as a non-rectangular shape. There's some Fibonacci series in there, anything but rectangular. Some words about us. As I said, I left the corporate world and I found a rundown place where we created Loft, and we're across from the UN on the east side of Manhattan, actually in Long Island City. And we've been grown to a real office. Probably we're no longer a startup. We're about 16 people from 10 different countries. So this is our office room. This is the old gas pipe. My neighbor is Murakami, the famous Asian artist. And on the other side, we have a brewery. So twice a week, it smells like fresh beer where we are. So what we did last year is the 2D tryout crazy little test on that sunflower model as a terrace. And we just felt like, let's keep all these old chimneys and the roughness and just build something around it. What I'm interested in is seeing if structures can maintain what is there and kind of grow into it, rather than taking everything down and being rectangular. And so the logo, when you look at it, is based on sunflower growth. And the flower grows in this very interesting pattern that you see on the screen. Yes, you're better than I in this. We have grasshopper now. We still need to get a technical handle in this. So the initial idea from the natural shape still has to be transformed to some degree into something technically, because we want to manufacture or produce it later on. And in that sense, we are working right now, and I do this on my personal R&D time, how to get a handle on these different shapes. And from the 2D, which we built after work hours and weekends, you see here that 2D terrace, which is based on a conventional deck structure, was already based on a digital fabrication. This is a marine plywood where we made the shape and then directly gave the CD to my friend across the street, where we have a wood maker, Tietz Bacon, and they just printed it. And then every piece has a number on the backside, and off you go. Very low tech. That's a 2D adaptive structure. It's quite nice in the winter time because the joints show up when the snow hits our terrace. This year, I'm a bit more ambitious. I want to make a 3D step. I want to try and see how we can use these shapes that maybe have advantages over conventional parallel grids by building a quarter of a sphere, a dome, a grid shell, as you see on the screen. And so what we need is, obviously one day this could be ETFE normatic pillows, because I don't have quadrangles that are all in one surface. But for now, I'm just interested in the initial nodes. Yes, I engineer all this. I've done this for years. But in this case, I'm interested in what are the connections about? How can we make these shapes economic and credible? And so we number it, we shift it, we move it around. Purposely, I take the center of the sunflower offset because it looks better. You also see you get really wide on the outside, really narrow on the inside. So there's some compromises on the parametrics that we need to figure out. And then MIT recently developed a laser printer. That's not the first one, but this one has fiber in it. So this is nylon and fiber, and we print both at the same time. And that gets us strength to almost close to aluminum. So the reason I buy this one is not because it's the fastest, it's actually slow, but we reach strength levels that we can really build with. And you can imagine, and maybe I show around some of these prototypes, what I'm after is to say the disadvantage of the sunflower is that I have millions of different or thousands of different geometrical connections to solve. But because the printer couldn't care less what they print, I'm using a modern 21st century technology, which is this one. Then I'm using our modern software tool, and then I'm using forms that are informed by nature. And the three together hopefully will get us to an interesting result. Now, first types, very ugly, but also we quickly figured out if you do a male-female connection, you cannot just put them together. There comes a point where you have no more room to put the next piece on. So what we're doing now is we're making a connection where we come off from the top with a 45-degree cut aluminum pipe. And the goal is all the complexity goes in here, and everything else is very conventional. Could be wood, could be steel, could be aluminum piping. We can build hooks, we can number this, we can integrate lighting. So what I'm saying is, why not let the 21st century technology print this and have everything else conventional? And I purposely brought you some where we had some burning issues. You can see some of the bridging here. So maybe you can just take those around and show to class. I just need them back. So those are 3 pieces. So where we are now, according to the geometry, I can always come down from above, and then I bolt through. That means whenever I need to replace a piece, I can just unbolt it. And this is engineered with finite elements. And again, all the geometrical irregularity is only taken in here. These are just very conventional cut drill pieces as we know them from the past.
So your parameters there are just the angle of the nose?
Yes. We can one day even vary the amount of fiber according to the stress in the piece. Currently we're orthotropic because the fiber, the strength, like the rebar, is going 2 directions, so we have one weaker direction. And also, as you know, if you've laser printed, you need the scaffolding, so when you have a hole, you have to work around it. But this will be open, it already is, so water can flow through, lighting could go through, we could add hooks for like later finishes and so forth. Not that complex, I'm just interested in the steps, and my plan is to roll this out on a larger scale. And this is what we are going to do. We've already marked up the walls, so Hilti hit anchors will be the start, and then we come forward and we're just touching at 2 points. And this will be then my personal research on the 3D adaptation of a nature shape into a grid shell dome. And just because I'm now giving this to my RPI students and other students, there's beautiful examples of shapes in nature for a long time. You all know these, the agave, sunflower. We have shapes that are breathtakingly amazing. And so I have the students take these nature forms and patterns and have them convert into shapes of structural design. One of my favorites is the fractal cabbage. So if you cook her this weekend, just cut it through and look at it again. It's quite interesting. So even Einstein said, look deep into nature and then you'll understand everything better. This is the Ludwiglia sediotis. It simply starts growing from the middle and then the leaves find a way. And not that I'm against geometrical Bauhaus architecture, but we should wonder why nature is never using the 90-degree angle. And we should maybe step back and say, maybe our technology is now ready to copy nature a bit more with 300 million years of experience. Huh? So I'm claiming there might be structures out there that are more efficient than rectangular beam column buildings coming from nature. I'm saying we might be ready that we have digital fabrication tools, which is Grasshopper, Rhino, Tekla, you name it. We are ready with a parametric approach, so we no longer have to shy away from a design that has 5,000 different pieces because we simply give it a number. And finally, maybe there is given courtyards, for example, in New York City with all the odd old buildings where an adaptive backwards approach into a given urban footprint is asking for something other than just a grid. I don't know yet. And if you see here, the disadvantage of my sunflower is that you get very wide on the outside. So there might be other shapes. We looked at the aloe here and there, the agave, where we do not get so wide with the base, the further we get away from the center of the geometry. We'll see, don't know yet. Or in other words, historically, 19th century, I love these early steel structures. Why? Because we put all the money in saving material. The material was where the money was. So labor was less important. So we were building according to force flow. That's why a lot of these systems are so delicate. 20th century, my criticism is, yes, we made very fast progress, but the labor was all in the building, the cost was in the labor, so we stopped optimizing material and we ended up with very repetitive, sometimes raw systems. So perhaps we're now ready to go back and combine the two, where we have an intelligence approach how we make things, and at the same time allow ourselves to be freeform, follow arches, shells, and domes. And the example, as I said earlier, one more, craftsmanship, some elegant stuff in the 19th century, limited, 20th century, very repetitive, very unitized, maybe 21st century, something I'm doing with you, Tristan, in the Miami Design District, which is based on some more organic architectural vision. We're just starting, but this is reality. This is about 30 foot tall. This is in Edmonton, Canada. These are self-carrying skins, and the skins are made out of cold bent aluminum or steel thin plates that we program and then rivet them together. It starts, this is Marc Fornes, my friend in Brooklyn. It starts with small scale models, maybe this big. It starts with a Revit Rhino grasshopper program, and then every piece, as arbitrary as it looks, actually is exactly defined. And the power of the experience is the light as it goes through, the color, and the thinness. So there's not a single beam, I-beam, column member. Everything is 1/8 of an inch plate, which is shindled and riveted on top of each other. The role of the engineer here is especially stability. You may have heard of plate buckling, lateral torsional buckling, column buckling. Because it's so thin and it gets compression from wind and snow, we need to make the curvature sufficient that it doesn't pop away, it doesn't buckle out. And that is what our contribution from the engineering side is. So when Marc sends us something, I tell him, this is where it would buckle, this is where it would buckle. We go back, we change the shape. So I'm not the designer, but I'm the support in terms of creating that shape so it doesn't fail when it's a windy day or it's snowy. We have evolved. We're now building longer strips to reduce labor. It's still fairly labor intensive, but we don't need any scaffolding. He just comes up off the ground and we build everything ourselves. He wins all over the world right now. We did one in France. We did one in Texas. This one is in Rhode Island based on the Candela double curved hyperbolic paraboloid. And all of these things are about 20 to 30 feet tall. This one is the one in San Antonio. It's now being built. We're evolving. We're trying to kink a bit more. He does not allow me to ever close the leg. I always back him for closed shapes because they have a higher capacity and buckle at a higher load. But because of this being skins and being open, we can only kink it. So we're introducing a certain amount of kink. And then, again, this is my engineering support. These are so-called shell finite elements to help him figure out how to exactly build it. So the process is we do the footing, then we come up with these prefabbed elements. They come off the truck, they have a number, they have a color. This is anodized or polyester powder coated finish. And then it fits together quite magically. Of course, we're using principles like true arches, shell structures. The physics of nature is still valid. So you can't beat gravity's pointing down, for example. And so the ship industry now starts to get interested, and we're building the entrance of the largest cruise ship in the world to come. And as I said, it's so powerful, the language, and now we're tesselating it, we're making openings in it, that a lot of people in the world like to have one of those. And again here, the basic idea is to try new shapes, try new forms, and then be not 19th century, but be 21st century at the same time. The Very Many is the website. If you're interested, Marc Fornes, there's all the other sculptures online. And since I'm in Georgia Tech, I also work with one of your own, with Volkan Alkanoglu. I don't know if he's still here, but I do all his sculptural work as a supportive engineer. I picked one he recently did in Denver, Colorado, called the Supernova. A person who lives here or used to live here or teach here in your school. And then it gets funny and surprising. Then it gets all of a sudden, I'm not saying mainstream, but the LAX airport on the West Coast felt that their airports were too boring and they have no good retail concept. And so Starbucks says to friends of mine from Arctura, they do metalwork, give me something with a bit of identity. Give me something different. And I call this the return of the rivet, because riveting was old-fashioned. Everybody wants to weld and bolt. But since these plates are so thin, welding would distort the piece and bolting would be overkill. So we're actually riveting these pieces out of flat, very thin aluminum bars, and then do the engineering to create things like canopies where people are drawn to buy the coffee for Starbucks. Note that because it's so slender, again, that's why we save a lot of money. We don't need, all we need is we need punched flat metal and a computer that tells you CNC where to cut it. Then we engineer how many rivets we need, we shoot them, and everything else, I mean, there's more to it, but it's relatively straightforward. There aren't any engineers here, but what we still do is we validate deflections, stresses, stability, frequencies, and connections. So the system in itself still needs to be verified to code. This one even had earthquake loading to California standards.
So what governed in that side?
Stability. The problem is when you have cantilevers with negative moments, you pop over. It's always the load cases that you don't reach the stress limit, but you fail in so-called stability modes. And that is what we help, and then go back and change the system. So these failures happen way above the load level that you get, even in an earthquake. And again, this funny return of the rivet, the old-fashioned pistol, and you just tell the fabricator how many rivets you need in certain areas of the canopy. And then you verify shear and tension and so forth to code. And then the yogurt guy liked it, and he says, what do you have, Starbucks? I want something too. So we gave Pinkberry another pavilion. This one is more shell-like, but nevertheless, it's basically, except that one column, it's all out of flat plate material, which is very non-expensive. And we do prefabrication approach as much as possible is fabricated in the shop, and only a few rivets then are done on site. And now they're starting to work with artists, and the next step we're trying is facades, like rain screen systems, where we can adapt that as a next step, and also canopies. We're not yet watertight, obviously, but we'll see where that leads us. Now back to Atlanta, Georgia. There's a very innovative mold maker and ductile fabricator called Dex Industries. And this gentleman here is the brain behind a lot of the complex molds. It's a new type of concrete that no more needs rebar. It is very dense and it has fibers in it. And because it's dense, architects know that the haptic feeling of this is like a corian, very smooth, very fine. And so the challenge was Louis Vuitton in Florida wanted to overclad a retail store and give it their unique identity with the flowers of their fashion paddles. And this was very much produced all here in Atlanta. You see the negative molds, these are silicon molds. We actually did the corner piece in one open mold piece, that's why there's no misalignment. And my role is to make clever substructures that are adjustable and engineer everything so it can work. This is the cross section. The fibers, you can't really see them, but there's a 4 to 5% fiber mix, EVA fibers, in that special concrete. And that's why you can make such fine, elegant molds with it. You see that on the left. You could never do this with conventional concrete. It would crack off. And again, this is now getting traction by other architects who have very nice ideas. This is a Jordan Brown furniture store. We can do different recess molds. This is all here in Atlanta. And we can do embossed, we can do perforations to create new type of facade panels that we couldn't have done without that material some 10, 15 years ago. And we use so-called undercut technology where we fix in certain points. We put the hurricane wind on it and make sure that everything is adjustable. And then you can see results like this, very pleasing. Architect was very happy with the design freedom you have, because from a simple panel, all of a sudden you have different depth and layers. Oh, this is my engineering headache, because I still have to convince the authorities that it is safe and that it's not falling down. So we use so-called small-scale tests and finite elements, and we have reference projects to convince the code people that we can do it. It needs to be drawn. A lot of my work is facade engineering. This is an example of that. So how do you fix it? Well, you see a hidden undercut. This would be the cross-section of the piece. But you don't want constraints in the panel. So there's an adjustability, like a clip and a railing and a set screw. There's wind load only supports. There's dead load supports. And that type of stuff needs to be fixed into concrete, into brick. So all the specifications of how you actually put something like that on a building is called facade engineering. And again, I'm not the designer. I'm the supporting role to push that architecture through and help make it happen. Nike likes it now. So these are early examples. In South Beach, we're going to make a screen. Again, they're going to make the swoosh sign now out of Ductal, 2 of them. And this entire thing is made out of Ductal to be produced right here in Atlanta. One of my favorites is, I hope you like that too, is a little retail store where we're using big Ductal panels to create an outer screen and have 3 metal doors in it to attract customers into the store. Again, that will be Ductal over a metal substructure. And here you see the horizontal section. If it doesn't get value engineered, it will be probably the first of its kind in New York City. And finally, Culture Shed. Elizabeth Diller, she runs Diller Scofidio Renfro, has designed a very interesting public art space on the Hudson Yard in the west side of New York City, where it's meant for the public to do performances, fashion shows, cinema evenings, and the entire outer skin moves on rollers back and forth. So it will be like a flea market. Because the weight was so limited, it all has ETFE pillows on the outside, a bit like the Arctic in San Francisco, and then we're doing all the cable walls and glass and canopies on the outside of that building. We get certain wind loads. We look at cable deflections, that the compatibility of the glass isn't violated, and did a lot of work in the background to make this happen. And we know also that we can twist glass to a certain limit. This is double glazed laminated glass. So there's a lot of modern technology that you never see. These are the cable tie downs that later hold up the thin facade. But nevertheless, we're very proud as New Yorkers to get a really new hype space. I know it will be a success. Just the identity of that moving mega frame coming in and out. It sits in between the new boring high-rises, the commercial side of things, but this is right by the north end of the High Line on 32nd Street. And it's also for everybody. It is not a private space, but the public of New York is allowed to come in there and perform. Thank you very much. That was it. Was that too fast? Yes?
Well, I'll start with a question about education. There might be 3 architects in this room who want to be structural engineers. And when I teach structural engineers, there might be 3 structural engineers in those rooms who want to be architects. So you're a hybrid. So what would you encourage young people to do if they see themselves wanting to have the knowledge that you have? Let's do it.
Well, my story is I started engineering. I was pretty fast and was miserable because it was just math and it was very theoretical. And then I also did some architectural years, but I realized I'm not super talented as a designer. So we're good in seeing a design, getting something, and then making that happen. And then we're very strong and very stringent in a way, very rigorous, right? So I would almost argue you probably want to do a little bit of both. So maybe if you're an architect, do maybe a couple classes that you teach. I just learned that you teach that. Or if you're an engineer, do a few classes on architecture. I mean, we know historically, you know that, right? The disciplines, when did we split? See, 15th, 16th century, if you build a cathedral, we were all one. We were even the builder at the same time. We split in the Industrial Revolution. When did that take place, roughly? 18th century, right? Why? Because what did we discover? Steel, concrete, and then the architect became the artsy person and the engineer became the math nerd. And really, but we're getting along well now, but really for me, it's in the overlap. So for me, the separation makes you incomplete. That's why I like your question, yeah.
But if I could add to that, I mean, I think it's also a question of fluency, because people like you and then I think people like Jim Kinney's, right? Like the best structural engineers had some amount of architectural training.
Yeah.
It's not that they want to be architects, but they at least have fluency. They can have a conversation, and it's not me doing my thing and you doing your thing, but there's actually a common ground.
See, when you are a young engineer and the architect tells you, I'm thinking of a wall, I now understand the language means I have a calm surface, I have an expression to a wall. When I hear a wall, I'm thinking it's a diaphragm. So I don't even understand the language initially. So even the language doesn't match. So there's many things you can learn over time, right? Yeah. Another thing is also, do you like each other? Sometimes I don't like somebody. But like this guy, he had fired all the previous engineers, including Arab. He fired everybody, but he has not fired us yet. So we like each other. And also, I, of course, make zero money on this. I lose money, but I don't care because it's exciting and I know this is going somewhere, you know. So you don't have to work against your instinct. And that's, I think, on a good corporation, which can be helpful when you generally like each other. So, yes.
I have a question about the product that you guys came up with for the joint modifications.
Yes.
Ignoring the 90-degree angle. Where do you see that going? Do you see that? I mean, I know you're using it in a canopy and just testing the product right now. Do you think that it could evolve into something that's productive in our designs as far as?
I have two things in mind. One is I noticed for years all these shitty courtyards, excuse my English, in New York City, and you will know that, where these awkward building volumes are there. And I'm trying to define that as a given boundary condition and go backwards with the structure, a bit like the British Museum. You know that in London, where they built the beautiful grid shell, they had a given awkward situation. So that's one. And secondly, I'm dreaming a little bit to go to some retail store, because I do a lot of, like Marc Jacobs and Valentine, we do fashion stores, where I'm trying to sell them an identity. So I'm thinking maybe following something like this or this, that we can maybe come up with exhibition pavilions which are based on nature growth. Maybe an organic men's cream or women's cream or something where somebody likes the idea, and then roll it out as a parametric product. I don't have the ambition yet for permanent structures because we don't have enough testing yet, but generally I think we're ready to try that. And then
Do you think that you would have to modify the geometric shape of the substance? Because right now it's in a triangular shape, sitting right against each other. Maybe changing, modifying that shape can make it more stronger, such as of a rectangular shape of where force is more distributed.
I hear you very much, and I told my students I'm going to be voyeuristically stealing their ideas, because currently I just gave them these shapes and said, if you're interested, roll with it. Because this is clearly a radial structure, this is clearly a Fibonacci structure. There's all different types, and we're trying to figure that out right now. It's a bit gimmick, but I'm sure that we will come up with some shapes that are beautiful and make sense. We'll see. Don't really know yet. Yeah. But what I do know is the filler material, if you think of the something like this, This will definitely be ETFE pillows for me, pneumatics, because these surfaces aren't in one plane. So I wouldn't go in with flat glass. It would be too much bending into shape. So this is just a trellis, but the next step we will make it waterproof. If we have longer spans, I need wider mullions, and then I can hide the profile, what you saw at the culture shed, and put pneumatic pillows in it, because the air, the balloon, can form into any cell, and then will be watertight as well. Does that? So yes, any triangularization, we already have done this for a long time, but the goal here is not to use triangles, and also the goal is, again, actually this is wrong, it shouldn't be square, but the goal is to weave yourself into some given footprint. That's the goal. Yeah. And this is quite fun too, because you learn, it shrinks, there's more to it than just say you print something.
What's the durability of this material from an environmental perspective?
It's nylon-based fiber, very lightweight.
To be resistant?
We are thinking to maybe paint it to make it long-term, but on a temporary structure, it's definitely good. I would say up to 5 years, I wouldn't have any problem with it. Very slow. One piece takes us 12 hours, crazy slow. But I bought it because it's the stronger one. If I take a normal one without fibers, then I don't have that engineering claim that I can really build with it.
So this is a dual head, there are two heads, one is depositing a fiber, one is depositing a polymer.
Yes.
Okay.
Yes.
Stitching. sort of,
Yes.
right?
I mean, there's got to be, part of the motivation to have these talks, and to buy the lunch and all of that, is to get us into some sort of dialogue, right? And that dialogue would then extend beyond this room and into the studios. So there's got to be some notions out there. I mean, 3D printing, this is the future. You guys all want to 3D print, right? I had a client the other day who told me, we should have just 3D printed the project and it would have been done a year ago. I told him, it would have been a different thing. So do you guys not have any ideas or sort of commentary on these technologies? Or design ideas?
Well, we have practitioners here. What we also face is the cost problem. You have to, it's a big thing to get this built because you have to convince somebody first. You have to have a client. So the old days, you were told, well, if you need 200 molds, castings, or expensive machine pieces, the cost is through the roof. So a lot of what we do is not just to be crazy, but actually use what we can now that we couldn't do 20 years ago.
Well, and the other
Yeah.
argument here, I mean, one can say this is sort of ridiculous because of the cost and time, but maybe you used the word gimmicky earlier. Maybe it's not gimmicky enough. Maybe in 20 years, 50 years from now, when we're out of materials, right? When the world is out of material, we can't put this much steel into a section anymore. We have to get it down to this much steel and use it much more efficiently and effectively. Maybe then there's really a very serious argument for human habitation and how we occupy the earth and use our resources. I mean, is that something that you're interested in?
I like the fact that this is all bolted, because bolting you can always unbolt. Everything glued or welded is very bad for recycling. But once everything's bolted, you just unbolt it and you have your basic material back.
Designed for disassembly.
Yes. The truth is also my rent expires in 5 years. We might be torn down earlier. So I gear everything for 5-year lifetime.
You can take an inventory of member links, right? And you could plug that into your system and just reprint all the nodes and redeploy. It could be adaptive in that sense.
Yeah.
Okay, well, Will, thank you. This was phenomenal. Wonderful work. Thank you.
Thank you.